is going to be a function, right, from a Boolean vector to a bool. So how should I use this inside there? So I want to use R. Okay, very good. Excellent. Okay, I'm going to call it at the tail of the vector. Okay, can't see that. Okay, so what will happen is essentially your at the bottom of your recursion you have head of V, and then you come out, you plug into the V tail of V, and then it will basically mean you're getting like the second or third or whatever element you need. Yeah. Yes.
How does box happen?
How does box happen? Well, so box in this example here, okay, what box does, it will ensure that what you're generating does not depend on this entity. Okay? So the traditional implementation you might have had in mind is that you say n of 0, okay, and the vector, okay, you say head of V, and then you say head of successor of n, V, and then you say, well, it's going to be, what is it going to be? N of the tail of vector. Okay. So that means if I run here n of 1, let's say, okay, what do I get back? Well, I'm going to get back a function that still waits for the V, and then computes n of 0, tail of V. So it will not compute this because in a functional language we never evaluate inside the function block. Now here, so that means if you run this partially, you're not going to get code that is being okay. So build a compiler, for example, right, you would still need to store n, for example, somewhere. Right? Because then you need a pointer to that n function, otherwise you can't run this code. Right? Now here this is different. Okay, so if I will call n of 1, okay, so what will happen is it will call let box of R, and then it will say n of 0 in box, okay, and it has the function R, okay, which still waits to be applied to this tail vector. But now I can run, okay, this will continue to evaluate, and what I will get for n of 0 I know, okay, n of 0 will be a function of head of V, so we have here let box of R is going to be a box of this function that goes to head of V. In this other function, box fun V goes to R assigned to tail of V. Okay, and what will this return to? Well, it will paste for this R in this function. Okay. So the result I will get is box of a function that will then have another function sitting inside here. So in some sense the result, in some sense the vector V0, which will return head of V0, which will be applied to the tail of V. So this will be the function V0, return head of V0, and it's going to be applied to the tail of V. So it's still not quite what we expected. What did you expect? What do you hope for? Like that? Head of tail, right? Yeah. Head of tail is what we would want there. So this is still not quite. Okay, and it is because because we have here a reader exiting that will not evaluate because you're it's sitting under a function. With me so far? Yes?
So to rephrase what you said earlier, I think, so in the traditional style, if you partially apply n, the compiler has to close over n because n sort of stays inside. But when we write it in the other way, there's no closure over n.
That's right, there's no closure over n. So that's a good thing of this program, right? It's completely independent, doesn't require ends anymore. I can do whatever, I can garbage collect ends or remove it, and I can send this piece of code to you, you don't need ends, okay? You can still run it. It will do the right thing, okay? But it is sort of, I mean, since we, in some sense in functional programming, we don't really inspect programs, we're mostly interested in running it, you might say, well, I don't care. Okay. It'll run independently and it'll compute the right result. But if you want to empower, like sometimes we do want to actually pattern match on code that we have generated. Okay? Because we want to sort of have programmers write their own compiler optimizations, for example. And in that case, we might not be super happy with this representation. Okay? We'd like to have something that is saying like head of a tail. And the cause of this is essentially how we define validity and how we define box. So this is essentially what the state of the reconstruction model, or the judgmental reconstruction of model logic was around 2000. Okay. And then people were like, okay, if you need these optimizations inside, well, run just an optimizer later on, okay, and or maybe we don't care, okay. But it wasn't really giving a logical foundation for how we could think about this in a better way. So this is where contextual types come in. So we are not talking necessarily about closed objects anymore. What we want to talk about is actually open objects. So 5 minutes. All right. So here's the gist again. So I want to not only talk about closed things, I want to say they can be open with respect to some local variables. Okay, so that means my validity is not going to be completely absolute. Okay? I'm going to say that A is valid. Okay? I'm going to call this with respect to some assumptions psi. Okay? If I use these assumptions psi here in order to prove A. So intuitively what this means is instead of thinking of it as something that says box of a function, okay, we're going to think of this as a box that basically has already an assumption, A, true, and proves B true. And I'm going to use this kind of symbol here to distinguish it from our normal term style here. Because what will happen is that we're going to internalize a derivation that might depend on assumptions. Right? So normally truth is, when I say is the proposition A true, this proposition, the truth of this proposition we prove in the empty context. Right? As we go along, we introduce assumptions, but we make statements about propositions and statements that are in the empty context. So here we start out in the empty context. Okay? And any of the examples we've seen, right, here we start out in the empty context. We always make statements about things that are closed. But that is sort of not sufficient for many, many cases. So for example, I like cooking. So if you have a recipe that says in the first step, add flour, sugar, and eggs to your bowl. All right? So you have your bowl, you put in some eggs, you put in some flour, you put in some sugar. Great. So then it says in the next step, it says, add something. Okay? So we're in this situation here. So step 1 was add eggs, flour, and sugar. And step 2 is add something new, okay? Something else. And I know that it is a particular kind of liquid. Okay, so the type of this placeholder is a liquid. Could be water, could be milk, coffee, whatever. Okay? But it's going to be something, okay? It's a placeholder in this recipe. The thing is, it doesn't live in isolation, right? It needs to essentially be mingled with whatever is already in your bowl. In your bowl, there's eggs, flour, and sugar. So it's not an empty bowl that you're plugging in this liquid. Okay? You're pouring it into something that has something already in it. And so this situation happens a lot, right? So here you want to actually say, I'm pouring some liquid in the context where I have eggs, flours, and sugar. So this was the type, but the context in which it lives is eggs, flour, and sugar. And the contextual type essentially says, I'm pouring in liquid in the context where I have eggs, flour, and sugar. Okay? So the type of this thing is going to be, it's going to be a liquid, okay, where I have eggs, flour, and sugar. And so this is going to be the type of what this placeholder is. So this happens a lot. Okay? It happens in programs because I want to, for example, describe, as I'm editing programs, I'm doing writing partial programs, partial in the sense that they're not complete, incomplete programs. Okay? So I might now I'm running out of words. I might write something, some program that says on-X, okay, and then I have here some placeholder that then adds X to it. Okay. Well, what is this guy? Okay. Well, it will be some integer. Okay, that's true. Okay, it will be some int. But it's not only 3, 4, 77, 42, right? It can be a program that could be, for example, an X. That would be a perfectly valid instantiation of this thing. So what I'm saying is I'm going to have an integer that lives, possibly, I can use an X from this context where I have already an X. That happens in proofs too, okay? Any of your goals in ACTA and a talk, okay? You have some assumptions you've already introduced, you have your goal, and it shows it to you even, right? Here are my gazillions of assumptions, blah, 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 H1, H2, H7, and then I have my goal. Well, what you're now filling in is something that depends on all these assumptions, right? You get some of these. So what you have actually as a goal in your, as you're developing is a contextual type. Okay? It is the type named your goal in the context of these assumptions. So, okay, to finish this discussion, I think I'll spend some time writing. Okay, I'm going to talk more about contextual types. And just to sort of say where this plays a role, it plays a role in providing more optimized and better representations of these programs that have not these reducers in it. Cyrus Omar has used contextual types for live programming in this programming environment Hazel, okay, to represent sort of the fact that your state of this program remains null type as you're editing it. They most recently have a paper where they want to use this idea of code generation, contextualized code generation for LLMs to avoid sort of that LLMs generate and hallucinate code. Okay? So because we want to make sure this is actually something that is meaningful that you plug in. Okay? It doesn't contain W, it doesn't contain Y, because that's not meaningful. Okay? We've used this idea to describe higher order unification and meta variables. We've used it in proof search, and we've also used it as a basis of the Beluga proof system. So we essentially want to also have a notion of derivations, where derivations are really, you have some assumptions and you're proving some kind of goal. Last question, and then I want to go to lunch. Yes?
Is there a connection between this and dependent type?
Yes, we can make this all dependently typed. So, in fact, so there are multiple versions of this dependently typed thing. The short answer. So the contextual modal type theory paper in 2008, we presented one version of this dependently typed. Most recently, probably the work by my PhD student Jason Wu has built a modal dependent type theory that also has let box on it, okay, and supports Gaussian matching on these kind of objects that you have inside the box. So you can think of this as a foundation for doing for meta programming in systems like COP or ACTA. And if you don't like the let box, so there's a alternative formulation of this model logic, which essentially is closer to the Kripke style model theory. That also Frank and Rowan actually showed early on for a simply typed case. And they showed that it was equivalent to this one. Okay. And we extended that to a dependently typed foundation. And that's a general functional programming paper. There's also variations of this where we don't completely separate these kind of two zones. Okay, so Gerald Houston, for example, Randall Houston has a formulation where you have blocks, okay? But it's closer to the Kripke style formulation than what I'm showing you here. And these blocks are always syntactic side conditions, okay? So it's a way of dealing with it, but I find this formulation particularly nice because it has particularly nice substitution properties and particularly all behave. But there are certainly also we can make this work for box on box for closer to programming methods practice as well. I can share all these papers in the Slack channel with you guys. Okay, and then on Friday I will talk a little bit more about the contextual modality. And then we can talk about the linear modalities. I think Valeria is preparing a graph for me again tomorrow, a little bit. Again, this is talking about linear type systems. And then hopefully on Saturday we can sort of come up with a unifying logic where we actually can represent box, linear, and then your brain will work. Then you can go and chill on Sunday. All right?